In this example problem from Chapter 8, we're looking for the eigenvalues and eigenvectors of this symmetric 2 by 2 matrix. We'll start out the problem by calculating the determinant, where we subtract lambda off each of the diagonal terms and setting that determinant equal to 0 to get our characteristic equation. When we expand this, we get 2 minus lambda squared minus 1, and that's set equal to 0, so we get 4 minus 4 lambda plus lambda squared minus 1, and that's all set equal to 0, and I can calculate that we have 3 minus 4 lambda plus lambda squared. Again, we can factor this by sight, but if you need to use the quadratic equation, then by all means you're welcome to employ it. I can see that the correct answer is, I can find the roots and factor this as lambda minus 3 times lambda minus 1, and the roots or eigenvalues are 3 and 1. For each of those eigenvalues, we now need to find the associated eigenvector, and we can do that by setting up the system of equations that's defined by we're going to subtract our particular value of lambda from each of the diagonal terms. So we have 2 minus lambda minus 1 minus 1, 2 minus lambda multiplied by our x vector, and that's going to be set equal to the 0 vector. So for us, that works out to be a system of equations for lambda equals 3. That's the first eigenvalue that will apply. We get a result of minus 1, minus 1, minus 1, 2 minus 3 is minus 1, and I have the b vector coming in and forming that last column. And after Gaussian elimination, this can be reduced to minus 1, 0, and our last row is 0, because it's really just the same as the first one. And this tells us that x1 is equal to minus x2, or minus 1, 1 is our eigenvector for lambda equals 3. And we have one of our eigenvalues and eigenvectors. Now let's repeat this step, this time for the other eigenvalue. So now for lambda equals 1, we just have to repeat that procedure, and we're going to subtract 1 from each of the diagonal terms, so 2 minus 1, and we have the off diagonal terms, and then 2 minus 1, and that gives us the system of equations 1 minus 1, 0, minus 1, 1, 0. When we apply Gaussian elimination, this is going to easily reduce to 1 minus 1, 0. You just add row 1 and row 2 to eliminate row 2 completely, and this is saying that x1 is equal x2, or our other eigenvector is 1, 1 for lambda equals 1. So we found our 2 eigenvalues and our 2 eigenvectors shown right here. There's our pair of eigenvectors and eigenvalues. successfully identified.